So let's get started. I'm filling in for Simiao today, and this is the second lecture, I think, in this series. And this one is on counterfactuals and potential outcomes. And this actually forms the basis of basically everything that's done later on in the class. How we think about what a causal effect is, how do we define it, and how do we estimate it. And sorry, my name is Nikhil. If you don't know me, I lead a research group here. So the slides are very ugly, but I will also spend some time writing stuff here. And stop me at any time if you have questions. We have, I think, 2 hours, and it's not too much material. So the goal of this class is the first thing is, how do we even define what a causal effect is? What are the important parts of the causal effect? What are kind of the building blocks of a causal effect? What is what's called the fundamental challenge of causal inference, a very bold title. And how does randomization, the typical way we think about estimating causal effects in public health, how does randomization solve that problem? I think that's really important to understand, particularly because it helps you think about how an observational study might also give you causal effects. And the last and potentially most important is, what are the main assumptions you need for causal inference? And I'll talk here about kind of broad assumptions, but for each specific method that you go into later in the class, they have their specific assumptions, but they're all kind of linked to these main broad ones. So the first thing you need in a causal effect is an outcome, the thing you care about measuring. And for everything we do today, I'm going to just use one example to keep things simple, and I'm going to look at systolic blood pressure. We denote this outcome oftentimes by Y, the capital letter Y, and the reason it's a capital letter is Y is a random variable. So Y doesn't necessarily represent one value. What it represents is the distribution of values of blood pressure that you can observe in a population. If we wanted to think about a specific value for Y, we often say this is the random variable, and it produces little values Y equals little y. So these could be your specific values. So that's an important thing to keep separate, because they can't see that. I just wrote Y equals little y on the board. It's an important thing to keep separate, that when you see a capital Y, it doesn't necessarily mean a specific value. It means a random variable that can take on lots of values. So if you want to talk about Y for any one individual, in this case it's I, Y for any one individual would just be lowercase y because it's a number. And the subscript there, I, means it's for individual I. The next big thing we need, obviously, is a treatment, the thing we care about estimating the causal effect of. And in this class for today, we'll talk about taking blood pressure medication as the main treatment. And we'll consider a binary treatment. In real life, you can often have treatments that take on many different values. But here, we're going to think about a very simplistic one of 1 is that you take medication, and 0 is that you don't take medication. So there's only 2 states of this treatment. The first question I have is, and I've kind of given you hints here, is this treatment well specified? If I just say taking blood pressure medication, this is an issue that we'll come back to later, but the first thing about estimating a causal effect is you need to specify in sufficient detail what your treatment is. For example, when I just said, okay, you take medications, what about taking it regularly versus every now and then? You think those would probably have different effects on your blood pressure, whether you took it every day or whether you took it when you felt like it. But when you say take blood pressure medication, that's not clear. So you should really be clear about when you mean that this treatment is being applied. There's also things like dosage is often a very important thing when it comes to medicine. Taking blood pressure medication at the correct dosage is something that's very different than taking at a lower dosage or higher dosage. So just saying takes blood pressure medication misses that too. Then there's multiple ways to lower blood pressure. I'm not sure, are all of you Dr. SC Whom or any of you Dr. Med students? Dr. Med, okay, cool. Then in that case, you'll know that there's multiple ways of lowering blood pressure. You have diuretics, thiazide diuretics, calcium channel blockers, ACE inhibitors, and each of these may have a different effect on blood pressure in terms of how much they lower it. So this point is really, really important, that questions like what is taking blood pressure medication is a treatment that we think is kind of poorly defined because it could mean so many different things. So if we revise our question, I'm going to start with the causal question today, and I'll say, what is the effect of taking blood pressure medication in the form of thiazide diuretics per protocol on blood pressure? So even this may have some vagueness in it, but let's pretend for now that this is not vague, that there's a protocol for how you should take thiazide diuretics. And what I mean when I say take blood pressure medication is that you're taking this one specific medication regularly at the dosage that it's recommended. So any questions so far? No? Okay. So what we think of, the first main point we have is something that's called a potential outcome, because our causal effect is a contrast of hypothetical states of the world. And the way we represent these hypothetical states is in this parentheses notation here. So here, y is your random variable, that is blood pressure in our case. Let's say it's systolic blood pressure. And when we put in parentheses 1, what we say is this is the distribution of blood pressure in the population when people take their blood pressure medication per protocol. 1 there means that treatment equals 1, the treatment that we've defined up here. And similarly, y here 0 means this is the distribution of blood pressure when that same population doesn't take their blood pressure medications per protocol. So this is the 2 hypothetical states of the world. 1 where everybody's taking their blood pressure medication the way they're supposed to be, and 1 where no one is taking their blood pressure medication the way it's supposed to be. I'm showing you the where 50% of the people take blood pressure the way they're supposed to be. But it's easiest to start thinking about this in terms of just the extremes. Everyone does what they're supposed to do, no one does what they're supposed to do. So what we're interested in really is the difference in y, systolic blood pressure, between 2 hypothetical states of the world. 1 where people took their meds, and 1 where those same people, and that's really the key thing, it's those same people didn't. It's not one population where took their meds and one population that didn't, and we're going to compare them. You think about this as that same group of people in 2 worlds. Sorry, if I'm going too fast to the slides, let me know and I'll slow down. So one way we think about defining our causal effect then is we can define causal contrasts or difference between these 2 hypothetical states of the world. And the obvious one for many people might be to look at a single individual eye. That's what we're seeing here when I say yi. This is the same individual, and ask, what is the difference between that individual's systolic blood pressure when they are taking medication per protocol versus in another world where they didn't take their medication per protocol? That is what we call an individual level treatment effect or an individual level causal effect. While this is actually really important for fields like personalized medicine, it's really hard to estimate from data. We often don't think about working with individual level causal effects. They're really hard to know. So what we think of often, and as population scientists, we often doesn't necessarily care about what happens for one specific individual, but what happens at the population level. So at the population level, we now have a contrast between the expected value of systolic blood pressure when everybody takes their medication and the expected value of systolic blood pressure when those same people don't. So this thing in brackets here, E, like this, is what we call the expected value. And the easiest way to think about it is it's just the mean, the population mean. So for today, we're going to think about everything in terms of populations. Obviously, when you have real data, you have samples, but it's easy to do this with populations first before moving to the samples. So E is expected value, and it just means the average. So what this is saying is we don't necessarily care about the difference in blood pressure between these 2 states of the world for that single person individual eye. What we want to know is if an entire population, or an entire population here could be all your patients with hypertension, your entire population took their blood pressure medication per protocol. On average, how different would their blood pressure be than if that same population of people didn't? So our focus today will be on what we call the average causal effect in terms of a difference. So what we're looking at now is just the difference in blood pressure. So this could be, for example, 130, and this could be 150. Your causal effect here would be 30. What that's really saying is, what is the expected value of blood pressure in our population when everybody takes it the way they're supposed to, minus the expected value in the population when those same people don't take it. if you think about, this is just a little math thing. If you have, instead of blood pressure, if we had an outcome like stroke, the risk of stroke, for example, that was a 0, 1 variable. Often we could say, if instead of y, if we said z is stroke, and it takes on two values, 0 and 1, well, the expected value of z, or the average of z, is actually just the prevalence, or the probability that z equals 1. So this also translates into what we call a prevalence difference. Yeah?
Yeah, like the estimated value and the mean value is not the same.
They're not the same. Here we're working with population values, so we will assume this is calculated at the population. In reality, you would estimate this thing from a sample. Yeah.
So like the estimate from sample is the estimate, and then if it's the real, like the mean means like the real number you know.
The true thing in the population. Yeah, exactly. That's the difference between what the expected value and the sample mean. So the sample mean is the thing that we estimate from data. And that's often our best guess of what's happening at the population level. The expected value is sometimes called the population mean or the population average, and that's usually unknowable. But the thing is, for this, if we start thinking about samples, we think about sampling variability, and for now we're just going to ignore that word, which is populations. But yeah, so the expected value of something that's 0, 1, like stroke, was also the probability that it equals 1. So it could be the prevalence of stroke. So like we defined this, we could very well define a ratio or a prevalence ratio, a causal prevalence ratio. We could instead say we're interested in the probability that z equals 1 when treatment is happening over the probability that z equals 1 when the same people are not taking their treatment. This would be a prevalence ratio, for example. But we'll deal with the difference for today. But it's really not. All you need are these little building blocks, and you can arrange them any way you want. So in words, this is how we talk about this. The difference in the average value of BP between a world where everyone in the population takes BP meds and a different world where everything is exactly the same, except that no one took their meds. The fundamental problem of causal inference, that big thing that has the big title, is that we only ever observe one world. We can't observe both of these states. And in that one world, some people take their medications and some people don't. So you don't have this thing where everybody's taking it in one world, then you go to a different version of that same world and everybody doesn't. We have the world as we have it, and in that some people take meds, some people don't. So to think about this a little bit further, you can think of there's two types of people in our population that we're interested in. We have the people that take their treatment, and we'll say T equals 1, and the people that don't take their treatment, T equals 0. If you take a patient population of people that should be on treatment in this very simplistic style of treatment, where it's just you take your thiazide diuretic per protocol or you don't, there's only two types of patients, those that take it, those that don't. So if we're after this first thing, this is, remember, the average value of blood pressure in a world where everybody is taking their blood pressure medication. Well, for the people that already take their treatment, we don't need to do anything. We know what their blood pressure value is going to be. So some of the people in the population do take their treatment. So for those people, we know what their expected blood pressure value when they're on treatment is. We can just look at them and say, that's your expected blood pressure value in treatment. The problem is, we also need to know what BP would look like for those who don't take it if they did. So all those people in our real population that don't take blood pressure medication, we need a measure of what it would look like for them if they did. And that's something we don't have. We can't observe that. The same thing exists for this other part of our causal effect. The expected value of blood pressure in the population when no one takes their medication. So a bunch of people in your population don't take their medication. So if you just look at them, you know for those people what their blood pressure value when they don't take medication is. It's just the observed one, because they're not taking it. But there's a bunch of people that do take it. So we have the converse problem now. There's a whole bunch of people in our population that are taking blood pressure, and we need to know what their BP would look like if they didn't. So the inference problem is often made like this. So in this is our real states of the world here. We talk about those T equals 0, not taking treatment, and T equals 1, taking treatment. And these are our two potential outcomes. The first one is outcome when the people don't take treatment, that's why it's in that zero, that parentheses with the 0, and the outcomes when they do take treatment. So the first thing is, if we try to fill in these cells, what is the expected value of blood pressure when you don't take treatment for the people that aren't taking treatment? I know it sounds like I'm saying a riddle, but think about that for a moment. You want to know the average blood pressure of when you're not taking treatment among those people that are not taking treatment. Yeah. It is their observed blood pressure, exactly. So this vertical line here is conditional. So this is the expected value of y conditional on not taking blood pressure. So that is a thing that we observe in the population. We can see that. Similarly, we could see the other diagonal too. If we want to know what blood pressure looks like when you take treatment, and we want to look at it among the people that are taking treatment, it's just their blood pressure value. So these two diagonals are observable. The issue is the off-diagonal elements. So you have a bunch of people that are not taking treatment, and you want to know what they would look like if they did take treatment. Well, unfortunately, you can't see that because all these people are in this state of the world. And right on the other side, we have a bunch of people that are taking treatment, but we want to know hypothetically, what would those people look like if they didn't take treatment? So that is also unobservable. So this is the big problem that we face here. We need to know all 4 of these cells, but we really can only observe 2 in data. So we refer to these 2 unobservable states of the world as counterfactuals. This is where the basis of counterfactual is. It's a hypothetical. It's a what if. We ask, what if all those people that are taking treatment actually existed in a world where they didn't take treatment? What would their blood pressure look like? And the other counterfactual is, what if all those people that aren't taking treatment, what if they did? What would their blood pressure look like? Those are the counterfactual states of the world that we can't actually observe. Any questions in the Zoom, people? No? Okay. So the question is, what is the association between treatment and blood pressure here? Something we can calculate in data all the time. How do you think about this? I'm really only giving you 2 pieces of information, so. Well, you could compare these 2 groups. The association between treatment and blood pressure is the difference in blood pressure between those people that take the treatment and the people that don't. I mean, you could, this is what we call the association. You could start putting control variables and think about it that way. But really, at the most basic level, we can observe these 2 populations in the world. We know the people that take blood pressure, and we know the people that don't. We can calculate their blood pressure, and we can subtract those 2 values. That is our association. The question for today, though, is, what is the effect of treatment on blood pressure? So which groups do you need to compare here? You have a guess. So we actually need to compare this group right here to this group right here. What we want to know is, what is the state of the world when no one takes treatment? And remember, some of those people actually exist in the data, but some of them are taking treatment. But we need to know what would these people look like if they were instead here? And we need to compare them to this. What is the state of the world when everyone takes treatment? Some of those people are, but some aren't. So we need something to move these people here. And this is the comparison of the causal effect. It's taking in 2 unobserved counterfactuals that the association doesn't. So this is exactly the thing we defined earlier. Does this make sense? Yeah.
Wouldn't the error be like the lower error be in the other direction?
Yeah, this is just to show that these are the 2 beats. Yeah, if you're doing y minus y0, then it could be the other. Yeah, definitely. So the absolute giant question of causal inference is, does the association equal the causal effect? Yeah.
But wouldn't that mean that those taking treatment in the group who epsilon 0 are kind of confounding variables in that case?
Say that again? This group here?
If you compare those those groups on the left side outcome when you don't take treatment, and you have some of them taking the treatment in that group, and you have a confounding variable because there are those who are taking the treatment which shouldn't.
It's not necessarily a confounding variable, it's that only a fraction of your population is doing what they're supposed to be doing, which is taking the variable or not taking it. There's a bunch of people for whom they're not doing that.
And this is neglectable.
It's not neglectable. If you neglect it, you make this distinction. You calculate the association. And that the big point is we actually need to know what's happening in this population, the one that we can't see. Yeah. I don't know if I answered your question.
No, it's okay.
Hopefully, if you go a little bit further, it'll become a little bit clearer.
It's clear and we'll clear up.
Sure.
The next.
So there's a way of visualizing this, and maybe this helps too. So if this is your real population of interest, some of those people are treated and some are untreated. In the association world, we compare the ones that are actually treated to the ones that are not treated. This is the comparison, the two sides of the world. In the causal effect world, we don't want just this half of the population that takes their medication and compare them to this half of the population that doesn't. We want to know what everybody looks like when they take it and what everybody looks like when they don't. And it's this halves here that are missing. So you can put this problem in math, and if this is too mathy, I'm happy to skip it. But think about the average value of blood pressure when everybody is taking their medication. Two things, the weighted average of two things. The first thing is the average value of blood pressure among those people that are already taking medication, T equals 1, if they were to take blood pressure medication. So we can observe this. We don't need to say they're taking it, what would happen if they did? Well, we know they're taking it, so we can just observe this. And the share of the population that falls in that category. The second piece, though, is that other part of the population. There's a whole bunch of people that aren't taking blood pressure medication, given by this share. And we need to know for those people, what would their value of blood pressure be if they instead took blood pressure medication. So this thing is observable. That's that diagonal element that we can see. This thing is counterfactual. We don't know what that is. We can't just directly observe that in the data. I don't want to hammer the point too long, but the reverse is true when you're looking at the expected value of blood pressure when no one takes the medication. We don't know what blood pressure, if for the people that are taking it, if they instead didn't take it is. We can't observe that. We can observe, though, what the blood pressure of people who don't take their medication would be if they didn't take it. It's just an observed value. So the issue we have in math is that we don't know these elements right here. So the one thought might be, can we just move? We need to know what these people who are taking treatment would look like if they didn't take treatment. Can we just put this value here? Can we say, well, we don't know what these people look like, but these people aren't taking treatment. So let's just fill in this value and say it's the same thing there. That we're just going to yeah. Oh, are you asking a question?
Oh, no,
no, yes.
Answer. I'm sorry.
Oh, no, yeah. So this is saying, like, those people that do take treatment, what they would look like if they didn't take treatment, can we just move in the value for the people that aren't taking treatment and say that's the guess that we have? And similarly, all these people that aren't taking treatment, their blood pressure when they do, can we just say, well, that's just going to be the blood pressure when those people, when we look at the people that aren't taking treatment. We have these two observables. Can we just duplicate this here and duplicate that there, and then we're good to go? Yeah.
I would say only you can defend the assumption that both populations are
exactly the same. So that's the issue. Can you actually estimate this counterfactual unknown as just the observed thing? And it becomes really dubious when you start to put this in words. Because you say, is the observed blood pressure of those people that take blood pressure medication a good estimate of what BP for those who don't take blood pressure medication would look like if they started taking them? And that's the question you have to ask yourself.
It's interesting. I mean, there might be other underlying risk factors, like you in the population who don't take medication, which may make the story.
Exactly. So I'm going to give you two scenarios, just like this, and just like which of those each. Think about which direction you think the bias would go. So I want to know what BP would look like if people that don't take meds started taking them. That's the question I'm interested in. And I go, okay, I'm going to do that by looking at all those people that do take medication and use that as my guess. And among those people, I see that their mean systolic blood pressure is 20 points lower than those that don't. Is that a good causal effect estimate? Well, in my first scenario, this is likely if you're someone who takes medication. You're probably in real life where it hasn't been assigned to you randomly in a study. If you're just someone in the population who takes medication, you're probably more likely to exercise, less likely to smoke, more likely to engage in preventive health checkups. Generally, your health is going to be better. So this is that issue that we know as confounding. And this is the idea that if this is the case, is this 20-point thing that I estimated too high or too low? Which direction would the bias run? It's too high. Because you see that, oh, the people that take blood pressure medication have a blood pressure that's 20 points lower than those that don't. But those people also do a ton of other things that make them healthier. So blood pressure might play one role in it, but all these other things are operating as well. And that's actually where the name confounding comes from, because you're confounding the true effect of multiple things into one. You could also, in your scenario, go the opposite direction. And this is something we observe a lot in developing countries, where medication usage is not very common for chronic conditions. So if you are someone that does take medication for hypertension, it's probably because you were in the hospital for a serious condition already, and the doctor said you really need to get your blood pressure in control. So for those people, is this 20 and is it too high or too low? It might be too low, right? You would say, okay, I'm going to look at those people that do take medication and their blood pressure is 20 points lower. Yeah, but they're also way sicker. So in reality, maybe their blood pressure, if they were the same people, would actually be even better than 20 points lower. But because they're sick, they're also the people with congestive heart failure. They're also the people with chronic kidney disease. Their blood pressure is not as higher than it would be in the counterfactual world. So this is that age-old scenario that people always call as causation, that correlation does not equal causation. But we want to talk about that phenomenon more rigorously, because our goal is to get at causation. We don't want to just like throw up our hands and say, well, it doesn't equal that, and we're done today. So the problem is, in observational research, the populations that do something and the populations that don't, whether that's you want your treatment to be exercise, whether you want it to be take medication, whether you want it to be less obese, the people that do something are often very different than the people that don't do something. And those differences also often affect their outcomes in things like health. So with blood pressure, we gave the example of those that have very low blood pressure are maybe also likely to have low BMI. So if you were to look at their cardiovascular risk and compare it to someone who has high blood pressure, you wouldn't really know is their cardiovascular risk lower because just of the blood pressure, just of the BMI, it'd be some combination of the two. You'd be confounding the effect of blood pressure and BMI. You could go the opposite direction too. So this thing actually has many different names, and depending on who teaches you, they'll call it something different. So it's worth knowing the different names. In medicine and epidemiology, we call it confounding. If you're a modern epidemiologist, you call it exchangeability. And we'll cover that concept a little in a few slides. If you're an economist, I'm sorry, my shoelace came untied, I keep stepping on it. If you're an economist, you would call this endogeneity. And that is because the two variables are produced by the same system. They're endogenously determined. And this is extremely confusing, so you should make sure to keep this clear. The social scientists will often refer to this as selection bias. But selection bias in medicine and epidemiology means something different. So if you hear someone say, yeah, that paper I read, they estimated a causal effect, but I think there was a lot of selection bias. You kind of need to ask yourself, who's telling me this? Is it an economist? Is it a social scientist? Or is it a medicine person? If it's an economist, they're worrying about unobserved variables that are different between these two populations. If they're a medical doctor, they might be saying, yeah, but that's some super weird population. Like you're comparing just patients here to some patient group here. They're select in some way. So that bias means something different. Just be aware of that. You'll get this in the lecture tomorrow, or the next lecture in 2 weeks, sorry. But one way to think about this, it's often visually drawn, is in something that they call a directed acyclic graph, the big word for a picture. and you would think about the effect of medication on blood pressure. So this arrow here is saying that medicine has an effect on blood pressure. And the way we think about confounding often is that, well, people who take medication are also more likely, healthy people who exercise take their medication, and these same people, because they exercise and they don't smoke and they don't drink, also have lower blood pressure medication. So we call this the structure of confounding, and that's something Simia will talk about next time, that because you have something that's causing both medication use and blood pressure, if you just compare the difference in blood pressure by medication, you're mixing up this thing's effect into it. You don't want this situation. The classic example of this is when you study differences in drinking across populations. In the older ways, they would say, okay, let's look at alcohol consumption and mortality. And initially people thought, like, wow, alcohol is extremely damaging. You get a really, really high value. But what they found is people that binge drink are also likely to chain smoke. So these two things are correlated with one another. And chain smoking, of course, affects your mortality risk. So maybe it's actually the case that alcohol isn't as bad as we think, because what happens when we just compare people who drink heavily and don't drink heavily is we're mixing up the effect of smoking in there. This alcohol and mortality is endogenous into the system somewhere. So this will be fast today. The important question today is, how does randomization solve this problem? And that's one big issue. Randomization doesn't magically create a counterfactual population that, okay, you know exactly what these people would look like. The reason it solves the problem is treatment in a randomized control trial is assigned randomly, and it's not based on characteristics that may influence health. So you never in a randomized trial say, like, I'm going to give the treatment disproportionately to smokers versus non-smokers. I'm going to give the treatment disproportionately to those people that are healthier than those who are not. That's just not done. That would be a very like a supervised randomized trial. So what this ensures is that because treatment was randomly assigned and wasn't done based on anything you knew about the person, that these type of situations wouldn't happen. You wouldn't observe a correlation between treatment and BP medications and, say, congestive heart failure, because you would expect that there's an equal amount of people with congestive heart failure in both the treatment and the control. You may not expect a correlation between BP and exercise, because there might be an equal amount of people who do regular exercise in both the treatment and control. And because there's an equal amount of people in both those groups, we say that on average, the treatment and control group are balanced in terms of their observable and unobservable values. And that's a really big advantage of randomization, is this thing. In an observational study, we can collect a bunch of data on people that we think matters. And we can try to adjust or control for that data in some way. But there's always this nagging feeling in the back of your head that there's something you missed. That there's some difference between the treatment and control group that you just forgot about or you weren't able to measure that's biasing or confounding your estimate. In a randomized control trial, because the treatment was given randomly, even the things you don't know, it can't be correlated with. The issue is here, and this is something we'll talk about briefly, is this on average. This means that, like, in theory, this should be the case. Many times in randomized control trials, you have imbalances by chance. And that's why if you read papers in medicine and health, the table 1 is always the balance table. It always shows you the difference in a bunch of observable characteristics between those who are and are not in the treatment group. And you really worry about a clinical trial if it's really imbalanced between the treatment and control group. Any questions? So I'll introduce this other word here. So when this happens, because we know that the difference in characteristics between the treatment and control group of both observed and unobserved is negligible in randomization, we can exchange the unobserved potential outcomes with observed data. So what we're saying is, if T is not just how it is in the population, but if we assigned T, this is treatment in a randomized trial, well, all those people in the randomized trial that got treatment, what would their average BP look like if they didn't get treatment? Well, we could just look at the average BP of those people that we didn't give treatment to. Because now treatment no longer is correlated with all those other variables that also influence blood pressure. And similarly, this is the one we often think about a lot. It's sometimes called the average treatment effect on the treated. All those people that didn't receive treatment in our randomized control trial, 50% of the population did not get treatment. But we want to know, what would their blood pressure have looked like if they got treatment? Because treatment was randomly assigned, we can just look at the blood pressure of those people that got treatment and say that is a good estimate. So if we go back to this thing and assume now that we ran a randomized control trial. So here, 50% of the population wasn't given the treatment, 50% of the population was given the treatment. This value right here, what is the value of blood pressure when those who didn't receive the treatment don't get the treatment? It's just the value of blood pressure for those people that didn't receive the treatment. These are things we could have observationally estimated. We wouldn't need a clinical trial for this, these two elements. But what is the blood pressure of those people that did get our treatment? If they did get our treatment, well, they got it, so it's just their blood pressure. But now, here's the real power. This off-diagonal element that used to be unobservable, we now say, well, what is the blood pressure of those people that didn't receive the treatment if they got the treatment? What would it have looked like? We can now just plug in this value because now we know that this group is not radically different than this group because we've randomized the treatment. So we're estimating an unobserved potential outcome with an observed data value, and we're able to make that leap because of randomization. So I think one common thing that people think of is that when you randomize, it's just causal. Like you have one population that is and isn't. The actual reasoning behind it is because those two populations are actually different from one another. They're different people. But the idea is that on average, they're not different. And that on average is really important. And it means that's why we can't estimate individual treatment effects. Because we can deal with averages. We can say on average, these two populations are similar, but we don't really know we don't really say like this guy is equal to this guy in the treatment group. We can't make that type of comparison. Does that make sense? So the thing is, and the reason behind this class is randomization is not perfect, and it has a lot of problems, and it has a lot of reasons why we might prefer an observational study. And the first is some treatments are just unethical to randomize. If we want to know what the effect of smoking on mortality is, we can't give some people cigarettes and say, please smoke these. It's just, if we want to know what the effect of getting a heart transplant on mortality is, we can't take a bunch of people that need a heart transplant and say, sorry, you're going to be the control group. We're just not going to do this for you. And that's a huge, probably the biggest reason why. But they're also really, really expensive and take a really, really long time. So if you wanted to know the 10-year mortality risk for a certain surgical procedure, you would actually have to randomize your patients to the procedures, give it to them, and then follow them for 10 years to get that mortality risk. And that's often, it is done, and those studies do exist, but there's very few of them. And those studies tend to, like, every time they exist, they get published in the best journal in the world. But even in these studies, randomized control trials, often because they are expensive, but also because they're administratively really hard to do. It's really hard to, like, ensure that you're randomizing and giving the correct treatment to everybody. They often deal with small populations, you know, hospital population, clinic population. And these populations are often not representative of the general population. So one way to think about this is, if you estimate a randomized control trial of what is the effect of blood pressure medication, thiazide diuretics per protocol on blood pressure, and you did that among your hospital population, does that actually equal the effect that you would see in the general population if every single person in the general population needed thiazide diuretics? And that's a leap. And that's often when we think about generalizability, and the term in our world, in the medical world, selection bias comes in. The hospital is somehow a select sample. When you look at people who just come to the hospital, they're fundamentally different in some ways than those people that are in the general population. Is there a world where that doesn't matter? Can you think of a world where that doesn't matter? When you have treatments that have the same effect on everybody. And some treatments do have the same effect on everybody. Like if you have a very clear biological pathway, it might be that regardless of who you are, whether you're highly educated or not, whether you have good health behaviors or not, the treatment works the same on everybody. In that case, the treatment estimated in a small sample should be the same as the general population. But that tends to be rare. The issue is if we see a difference in, and this is actually a major issue in causal inference, if you see a difference in an estimate that you estimated in a clinical trial, a small sample clinical trial, you have this tiny clinical trial hospital, you estimate some effect here. Great. And then you take a general population and you look at an observational study and you get this other effect here. We're often stuck in a world where this delta from the clinical trial does not equal the lambda in the general population. And we don't know how much of that is because of confounding and how much of that is because this population is really select and the effect of the drug in this population is different from the effect of the drug in the general population. That's an active area that's really hard to know. And this is a big trade-off that people face. So often health policy decisions are made by ask at the country level. So I don't know about Germany, but in the UK, they have a nationalized health system, and they decide which drugs they want to subsidize in the nationalized health system based on cost-effectiveness thresholds. So they say that the drug must meet the certain cost-effectiveness threshold, and then only will consider it and subsidize it to our patients. That cost-effectiveness threshold is done by simulating the entire UK population and saying how many lives would be saved if this entire population got our treatment. But often, they apply this. They take the entire UK population and say, this is the effect of the treatment for the entire UK population. And a big question, and the reason why people did this initially was this fear of confounding. They said, no, we can't look at an observational study of the general population because there's bias in the estimate, there's confounding. So let's take a really small sample hospital clinical trial where we know we've randomized it. But what that's ignoring and what people are now starting to realize is that there's a selection problem here too. So unless we really believe that the treatment works exactly the same way for everybody, it may actually be the case that these cost-effectiveness numbers are really wrong. Because when you simulate the entire UK population using an effect that you see in a tiny hospital, is that really the correct effect? And that's something that people are grappling with right now.
Can you give an example for a treatment which you would consider like this, like a treatment which you would say it works the same in everyone?
I am not a medical doctor, so I'm terrible at this. So actually, blood pressure is a good example of this, with the exception of people with like chronic kidney disease. Supposedly, a lot of studies find that lowering blood pressure has the same effect on mortality, regardless of everything else. So in blood pressure is like one rare example of this. There's a big meta-analysis that did this, that tried to see like, should you be giving blood pressure medication to people who are super old and have congestive heart failure? And the answer is yes, you should. Even though we might think like, well, they're frail, the medication might hurt them in a bad way, but it turns out it doesn't. That's one example, but that's basically the only one I know. Yeah, I think it's probably safer to assume that it wouldn't be than it would. Comorbidities are a really easy way to think about that. People in hospitals often have more comorbidities than the general population would. So if your effect varies based on comorbidities, then you have a problem. And it often does. So there's a couple study design issues too. A big one is called non-adherence to the protocol. You can randomize 50% of your people to take a drug, but you can't put the drug in their mouth and force them to swallow it. You can give it to them and say, you can please take this drug. You can even in some cases say, will you take this drug in front of me and I'll give you $10 or 10 euros. And that's done too. But you can't physically make somebody take a drug. So often what you have is non-adherence to the protocol. So if you see in your population, this is really problematic with things like exercise too, or diet, because you can tell people in a diet trial, everybody in the treatment arm, I need you to eat 1 steak a day. And everyone in the control arm, we have a vegetarian diet. You both can't force the treatment people to eat the steak every day. And you also can't force the people on the vegetarian diet to not eat the steak. So this non-adherence is really problematic, and it has, though, a kind of predictable effect. Can you guess what that is? Think about the example I just gave. I want to know, let's even take a more extreme one. I want to know the effect of smoking cessation on lung cancer or on stroke. And my treatment group is a bunch of people I say, don't smoke. And my control group is a bunch of people I say, do whatever you want. In reality, a bunch of those people that I've told not to smoke will smoke. And in reality, a bunch of people that I said, do whatever you want, might quit. So it makes your treatment and control groups look more similar than they should, which means you generally find smaller causal effects than the truth. So in this study, you'll find that, wow, okay, maybe smoking cessation doesn't have an effect on mortality. But that's because a bunch of your treatment people didn't do it, and a bunch of your control people did. And that creates that issue. It's called attenuation bias. You have, oops, sorry, did I not show this? You have non-random attrition. So this is the equivalent of confounding in a randomized control trial. If you have an outcome that's measured in the future, you give a bunch of people a treatment, a bunch of people a control, and you say, I want to look at your 5-year risk of developing heart disease. So I'm going to come back and look at you 5 years later. And 5 years later, a bunch of people have dropped out from the study or even died, maybe. If the people that drop out from a study are different from the people that don't drop out in a study, your randomization gets screwed. At that point, you now have a treatment and control group 5 years later that are no longer balanced, because certain types of people were more likely to drop out than others. And that if those same types of people that were more likely to drop out also have characteristics that affect their risk of heart disease, you've now introduced confounding into your randomized control trial. Yeah.
And that cannot be leveled out by statistics.
Usually no. It's usually extremely assumption heavy at that point. You like say, if this is the case and that, then this and this, then. So typically the way people will do that is they'll take a measurement and a whole bunch of pre-intervention variables, like 20 pre-intervention variables that they think are important for congestive heart failure. They might get your exercise, your blood pressure, your age, all those different things. And then at the end, there was non-random dropout. And it turns out that the people in the control group that dropped out were way more likely to be the older people. So we see like, oh man, actually it turns out that it doesn't have an effect. But that's because all the old people that would have seen the effect are not in your study anymore. So what you do is you look at your distribution at end line, where you have a bunch of old people, a bunch of middle-aged people, and a bunch of younger people. At baseline, sorry. And you look at your distribution at end line, where you don't have very many old people, but you have your middle-aged and your young people. And you upweight these older people. You say, you older guy, you now count for 2 people. You now count for 2.3 people. You now count for 4 people, to try to balance the number of people in each group. The issue is, it's confounding again. You can only balance things that you've measured and observed. If you don't measure something that matters, and those people are the ones that were more likely to drop out, you can't balance it. And chance imbalance is another problem. I mean, randomization works on average, but there's always the chance that you randomize and things are just imbalanced because of chance. This is usually pretty correctable though. You can just control for this in your model. So does that make any sense? Any questions? So after giving you all this, the whole goal of the class is to not randomize and think about how to estimate causal effects when you're not randomizing. And so that'll be the real challenge. So one thing that you should keep in mind when you're going through the other classes, like when you hear about regression discontinuity, when you hear about difference in difference, when you hear about fixed effects, is that schematic of potential outcomes we were thinking about. These studies are going to try and tell you, you do all these statistics, you do these cool things, you can estimate this thing. You can figure out what that is. And the question you have to ask yourself is, did the thing I estimate, is it actually this? Are there reasons why the thing I estimated might be different from this? And that's the whole game of causal inference. So there's 2 key assumptions, one that everyone kind of knows, and one that's a little bit more mysterious. The one that everyone knows, and I'm going to use now the fancy modern terminology for it, it's called exchangeability. It's also known as confounding, but it's a little bit more subtle than that. We think in a randomized trial, the potential outcomes, and the potential outcomes here are what would happen if you did take the drug and if you were assigned to not take the drug. The 2 worlds that we're talking about are independent from the actual values of the treatment. So what that means is, whether I gave you the treatment or not, has no bearing on what your blood pressure would look like if you didn't take the treatment. And we denote that with this little upside down T, it means independent. So we say the potential outcomes of Y are independent of the actual values of T. So that's hard to think about. So think about, the way to think about this is when that would not be the case in an observational study. In an observational study, you would have that, for example, T equals 1. And you would ask, is the fact that T equals 1, does this tell us something about Y other than treatment? And the answer is yeah, it does. The people that do take treatment are also more likely to do a bunch of other things, or they might be more likely to be more sick. So it tells us something. Whether or not someone takes treatment is not independent of what their outcomes would be if they didn't take treatment. In a randomized control trial, though, if I tell you T equals 1, can you tell me what the value, what blood pressure would look like if that person was in fact 0? Knowing the treatment tells you nothing about what they would look like in the counterfactual states because the treatment was randomly assigned. So this condition is that the outcome in the control group would have been the same as the outcome in the treatment group if they instead received the treatment. So if your control group, if you had given those people the treatment and you had your counterfactual, that's the same thing as those people that you did give the treatment to. That's the consequence of exchangeability. And the reason it's called exchangeability is an unobserved counterfactual outcome with an observed estimate from your data. And you can do this because you know that whether or not people got the treatment has nothing to do with what their values would be like in the different states. So think about what we do in an observational study now. So this is the first foray into an observational study, and it's something called conditional exchangeability. If we take our example of BMI medication and blood pressure, and let's say there's just one confounder. We're working in this world where there's only one thing that's confounding this relationship, and that's exercise. People that take their blood pressure medication are also more likely to exercise, which also affects their blood pressure. So if we just compare the difference between those two groups, we'd be mixing up the effect of exercising with the effect of taking a blood pressure medication. So what do we do in that case if there's just one confounder? We control for it or adjust for it. And usually the way we do that, at the most fundamental level, we know now that YT, so Y of 1, what the outcome would be if everyone took blood pressure medication and what it would be if everyone didn't, is not independent of their actual value. Knowing their actual value tells you something about what their blood pressure would look like. So people who take meds are maybe more likely to have lower BP because they also exercise. That's the example I just gave. So if we compare these BPs, the way we have to do this now is we have to control for exercise. And usually what we do is we say, okay, there's people who have vigorous exercise, moderate, and no. And we would stratify on those samples. We would only look, we would compare blood pressure between people that do and do not take medication within those high exercise people. And the reason for that is within that population, there's no difference in exercise between the people. Because you're looking only at those people that exercise heavily, if you compare then the difference in blood pressure, exercise can't be a confounder because it doesn't vary between those two groups. That's what we think of as stratified analysis. This is also kind of what's happening when you put like a variable into a regression. It's better to understand it this way because this is actually what the regression is trying to estimate. The regression is supposed to be a simplified version of stratification. The stratification at its core is how you control for confounding. You want to make sure there's no difference in the value of confounders between people that you make comparisons of. So this condition is called conditional exchangeability. And what it says is, this is not true. The potential outcomes of blood pressure are not independent of their actual treatment values overall. But if we condition on exercise, if we look within strata of exercise, if we only compare those people that have similar levels of exercise, then whether they got their treatment or not is now exchangeable. There's no more confounders in the world, and now we can make that comparison. Does that make sense? This is like the formal definition of controlling for. Yeah.
But wouldn't we have to adjust our question, our initial question, and compare two groups? One group taking the medication and doing exercise to another group only doing exercise. Wouldn't that be more precise?
Yeah, so you would.
You know what?
Yes, I see what you're saying. What you do is you calculate for each of those strata, and then you aggregate it back to the population. So you could look at these strata-specific effects. You could do this, and sometimes people do. They'll say, yes, now we actually have three groups of people: the heavy exercisers, the moderate, and the not. And we have an effect for each of these three people, and we can show those three. But what people usually do is they calculate those three effects, and then they average them back up to the population level to give one main effect. And that's your population average effect. Yeah. And the reason for this is often you have way more than just one strata. Like here, I've given you one confounder, exercise, and it has 3 values. In reality, exercise could have like 30 values, and you could have smoking, you could have other comorbidities, you could have age. So you end up having like hundreds of millions of substrata, all these little groups of people. Like you don't want to say, this is the effect of medication for age 61-year-olds who smoke moderately and exercise vigorously and live in this, like you don't want that type of statement. So ultimately what you do is you want to take it for every single person and then average it back to one understandable value. And that idea of multiple strata, like millions of strata, is actually why you use a regression. Because you can't actually stratify a population that many ways. You'd end up getting like no people in a bunch of these cells. And the regression solves that problem.
But it's also an issue of regression if you have too many control variables.
You have that issue too, but actually the issue of regression is it's a smoothing. So what you're saying in a regression is if you said age is one variable and exercise is another variable. In truth, what we call the non-parametric way of controlling for confounding is you want to make strata of both of those two things. So you want what's called a joint distribution